Hello and welcome to Introduction to Linux. My name's Ian McLoughlin, Prof McLoughlin, and today I'm going to take you through some things that I've been working on for many years. You're going to get a mix of listening to me, watching me on this video, but also using some of the PDF sheets that accompany this to try out things for yourself. So we'll talk about things now, and then at a time when it's indicated on the screen, you'll pause. Then you'll start to go through the PDF lab sheets, typing things and trying things for yourself. There'll be some tasks for you to complete. When you've done those tasks, flip back to this presentation and press continue and listen to the next part. In total there are 4 lab parts, and there'll be text and there'll be explanations describing each one at the appropriate time. Apart from the PDF sheet, obviously you're going to need a computer that's either running Linux or it's running something like VirtualBox, a virtualization program that lets you run Linux on it. I'm going to be using Ubuntu 18.04. Actually, you can use pretty much any version of Linux that's recent. You don't have to use Ubuntu, but I recommend it. It's very good. So what we're going to cover in this is some foundational material. It's either a crash course or it's a refresher for people who've already used Linux before, just to get familiar with how to use the Linux environment, how to interact with your computer when you're running Linux. We're going to look at some application development type stuff, so the things you need in order to build applications in industry. And then we're going to build skills for the future. That means you know where to go to for help. You have the basic knowledge to be able to pick up more information in future. But first of all, we'll go through some of the background. The initial introduction I want to make is to introduce you to Tux. Tux is the penguin, and it's the symbol for Linux. If you look on the display, there's a small penguin, and then there's something that doesn't look much like a penguin. It's actually a robot, and that's Android, and a large penguin, and then many penguins. And these really refer to different flavors of Linux or different uses of Linux. The small one is embedded Linux. It's the type of Linux you might get on a smartwatch. The Android is obvious. It's the type of Linux that you'd get on an Android mobile phone. The bigger standalone penguin represents desktop Linux. Not a lot of people use Linux on the desktop, but those people that do find it very full-featured and extremely solid operating system. The large group of penguins represents Linux server clusters. These are the things that power the internet. This is how you get your email, or how you access websites, how you do online banking and so on. It really does empower the internet that we have today. In general, Linux dominates in several spheres. First of all, if we look at the world's fastest supercomputers, there's a list of the top 500. It's called top500.org. All of them run Linux. It runs all of the world's most popular websites, the ones with the largest traffic, which are email. Domain names are primarily managed through Linux. It's used by NASA, space agencies and military systems. It's used where reliability is very important. Like I said, Android is pretty much Linux. In fact, it's the Linux kernel with a user interface and application manager layered on top of it. If you have an Android phone, you can very easily get to the Linux shell prompt. Everything inside the Android phone, apart from the graphical stuff, is handled by Linux. Big Linux systems, as I said about the top 500, these are dominating the world. And the graph that's shown here, it shows from around 1995 up until 2018 the number of the largest systems in the world that run Linux. Linux is the sort of pinkish colour on this graph, and we can see that most of the world's big computers were run with commercial UNIX operating systems. There was a blip around 2005 where Mac OS became popular, and in 2010 there's a blip when people tried to make Windows work in big computers, and they didn't work well. Linux has come to dominate. It is the best, it is the fastest, it is by far the most reliable, and I think it's also the easiest to use. We can't really escape ancient history, and in computers ancient history probably starts, well, at least in operating system terms, in 1969, and this is when UNIX was developed. Everything that's worth knowing about in computing comes from UNIX. Big companies like Sun Microsystems and HP, companies that don't really exist as such anymore, were based upon Unix operating systems. Apple adopted Unix in iOS, and Apple operating system, and iPad operating system, and so on. It dominates. And Linux itself is on the left, or towards the left-hand side of this diagram. It only really started in 1991. From that late-ish start, it was very quickly able to take over in most strands. Now, Linux is not Unix. Unix is a concept, and Linux was a, let's just say, something that tried to emulate the power of Unix. It's built upon Unix structures, it's built upon a Unix model. And these two things went hand in hand, the Unix model and the Linux way of doing things. And this is why the Linux operating system is so good. The inventor of Linux, Linus Torvalds, he calls it Linux. Many people call it Linux. I started using Linux a long time ago. I picked up the name, and most of the people like me started using Linux in the 1990s. We refer to it as Linux, but most people these days, they follow Linus Torvalds' pronunciation and call it Linux. I don't really mind what you call it. Why are there all these strands and versions of Unix and Linux? Well, this comes down to legal reasons. Linux mostly is under the GPL, the GNU General Public License, which is an open source license. It means that anybody can copy the software, anybody can use it, anybody can change it and recreate it and then market it as their own. It doesn't really matter. This is allowed. Open source is obviously beneficial because it allows people to use it. It allows people to understand what's happening inside there. It encourages improvement and innovation. With open source software, you can view the source code. You might not understand it, but you can learn software from viewing open source code. You can look for bugs and errors and backdoors and so on. You can expand your knowledge by looking at this. If you don't like how some open source software works, fine. Download the source code, change it and make it work perfectly for you. You can't do that with commercial software. Well, not without keeping away from prison. If you do find that there's some spyware or backdoors in your software, remove them. It's as simple as that. Open source allows you to change the software any way you want. But the real characteristics of what you're allowed to do are based upon the license. And there are hundreds, but the big ones are probably the GPL I already mentioned, the LGPL, the GNU Lesser General Public License, and the Mozilla Public License. They've got slightly different flavors, they allow slightly different things. And you can find out about those on the Wikipedia page and so on. So Linux itself, as I said, it's sort of derived from Unix, and it's become dominant in several domains. The places where it is most dominant are embedded systems, servers and controllers, or supercomputers and server farms. So each of these run an operating system called Linux, but they are different. I tend to work with embedded systems. Some of my colleagues tend to work with the supercomputers or server farms. It's the same operating system, but there's differences into how it's configured and how it's set up and how lean it is, how large the operating system is. The word Linux, we talk about it loosely as an operating system, but actually it's really the kernel of an operating system. And this study in 2002, there's nothing I have which is newer, was about Debian 2.2, a popular version of the Linux operating system, a popular distribution. And at that time it contained 55 million lines of source code. Now, just a point on this, if you were paying software developers to write 55 million lines of source code, it would cost you about €2 billion. I guess that's about $4 billion. Now, that's quite amazing because we get this for free. It costs us nothing. 71% of that was written in C, but only 8% of that 55 million lines of source code is the actual kernel, the actual Linux bit. The rest is a cluster of applications. It's like an ecosystem that surrounds the kernel. And today we really talk about Linux as being all of that stuff. Now, when should you use Linux? And I've said it's very good, but what are the characteristics that allow you to use this in different ways? And I would say that Linux is particularly good when you need something which is flexible, because you can modify it in so many ways. We've seen that. It runs on the tiniest to the very largest computers. Not many operating systems can do that. It's also good when you need standard support or protocol support, especially if you want to support some very strange protocol that nobody's ever heard of. If you are in the world of commercial operating systems and you need to support a strange protocol, you either have to write it yourself or you have to buy that from someone. In Linux, you just make use of the open source driver that supports that protocol. Linux is particularly good when you want fast time to market, or when you want to do something which is very complicated and it's multi-threaded, lots of things happening, or it uses high-level languages. Again, if you have a commercial operating system, you may well have to buy a language. If you want to program in some weird thing like Ada, then you probably have to buy a compiler. With Linux, you download it for free. And when you download and you develop something on Linux, you own it forever. There are no restrictive license rules that mean that you own this only if you keep paying a license fee year after year. On the other hand, there's some times when you shouldn't use Linux, or particularly embedded Linux. It is great, but if you want the absolute tiniest system, use an RTOS, something like MuCOS, a really small, less than 4 megabytes operating system that's quite functional. If you want incredibly fast startup time, use an RTOS. Or if you want the fastest interrupt response for a very hard real-time operating system, for a very hard real-time task, where if you wait too long a disaster could happen, then use an RTOS. Or if you want something that's so simple you only have one thread of execution, use an RTOS. Another time to use a commercial operating system is if you need someone to blame when your system goes wrong. There are many times when something crashes and we can just say, oh, that's Microsoft or whatever. You can always blame someone if you've paid for it. So that's enough background. I've talked enough. I'm wanting to get on to where we do some hands-on work. But first of all, we need to look at how to interact with and control Linux in practice. So part of that is looking at the world view of Linux. And this is a typical top-down view of the Linux operating system. We've got some RAM and some flash memory. We have a central processing unit, networking and so on. But there's a strange thing in here which I've coloured in yellow. It's the console. That's unusual. Now the word console, it comes from the early days of computing and it refers to where the operators sat when they controlled their computers. Have a look at this picture on the next page. The console is the thing that the operator is sat at. This is from sometime in the 1960s. And today, Linux still maintains this concept of a console, a central point of control. When you sit at the console, when you sat at the console, you would type and you would talk to the computer by typing commands. What's actually happening is the computer's running a program, and it's interpreting your commands, and that program is called a shell. It's the command line interface. In a Windows computer, it would be the DOS prompt. Most operating systems have got a command line interface of sorts, but in a Linux or Unix machine it's very important. Of course, being Unix based, there's not just one type of shell, there's hundreds. But the biggest ones are probably the bash shell, which most people choose to use, and sh, the basic shell that's available in all systems. I think that pretty much everything we're going to cover today would work on both of those. New shells tend to be compatible with these. So, we control our computer today not by sitting at a console, but by bringing up a console window and typing commands into the shell through that. We'll do that in a moment. Once we're sat at the console, once we're typing things into the shell window, then we can type two types of things in general. The first one is the commands that the shell understands, like I mentioned, and the second is the names of standalone programs. These are lots of utility programs that are standalone programs. For example, when we type something into the shell will look at what we've typed and it will try to interpret it. If it understands that as a command, it will execute it. If not, it will look for a standalone program with that name, which it will then execute. If we type help in the shell, it will list the available shell commands, but not the utility programs. We can type which something, so which space ps will tell us about the ps command. Is that a standalone command, or is that not a standalone command? Is it not something which is implemented by a standalone program? Most commands have inbuilt help, so I can type ps space minus help and it will give me some help information. But in general, the Unix way of getting help is either the man pages or the info pages. I can type man space ps, it will tell me about the ps command, or info space ps. If it's too much trouble to type that at the computer, you can just Google it. All of this information is on Google. But if you are at your computer and you're looking for a man page, which is really quick, you can scroll up and down with page up and page down keys, or up and down arrows, and you can press Q to quit from the man pages. In general, the man page system is categorized by different sections or numbers, and there's 9 of them shown here. Sometimes there's a command or a program that is resident in more than one section. For example, there might be a particular system call that also exists as a library call, and it would then be in sections 2 and 3 of the man page library. And by default, when you search for a particular program, it will give you the earliest page that it can find that program on. It's just something to be aware of. So in a moment we're going to do some hands-on stuff, and this will be part 1 of the lab sheets. It will be to familiarise ourselves with the environment and so on. I've said that you can have a standalone computer that runs Linux, or you can do this in VirtualBox. I'm going to use VirtualBox, and I'm going to use Ubuntu 18.04. That's the April 2018 version of Ubuntu. I'll show you how that happens. I'll switch to my VirtualBox. When you run the VirtualBox program, it shows something like this, and at the top here I can see where I've saved my Ubuntu 18.04. I'll start that. It will pop up a Ubuntu 18.04 window, which it will then restore. If you were doing this for the first time, it would boot up the Ubuntu PC virtually on your computer. That's pretty slow on my system when I've got video recording, lecture notes, virtualization, and who knows what else running. So I'm just using this method to restore something that I had up previously. So you boot up, log in, and you get the Linux Ubuntu desktop looking something like what my window is showing now. This is a graphical user interface. It's great, but it's not what we want for this lab. What we actually want is our console or terminal. So we click down to the bottom left and it shows a whole lot of applications. I could search at the top for terminal, but it's already shown on one of the icons here, so I'll just click it. And here's my terminal window. It is the 2000s equivalent of the 1960s console that somebody would sit at. And amazingly, I can type the same sort of commands that I would have been able to type if I was alive in 1965. There we go. Cute, quit that. So you're going to do this. You're going to try these things and stop this video right now. Once you've stopped it, then you boot into Linux and do what's on the PDF lab sheet. When you've done that, press continue and we'll get back to the second part of these notes. So welcome back. I hope you managed to do that okay. It's actually been about a week for me since I recorded the first part of this, and that's the benefit of being able to do this asynchronously. You also can pause and go away, make a coffee and come back if you wish. So you've done the first part of the hands-on. You'll have touched the Linux shell, you'll have typed some commands into bash and so on, and you might have found that there's some symbols that have a special meaning. And on this page I show quite a lot of these symbols. They have sometimes a context-sensitive meaning, but inside Linux, inside UNIX, they tend to have dedicated meanings associated with them. Like for example, the squiggle here is called a tilde. Usually that, if a tilde slash, it refers to your home directory. An asterisk is a wildcard and so on. I won't go through all of them. I'll just mention a few. Exclamation mark, as we'll see later, can be used to repeat a previous command. The quotation marks are interesting. The double quotation marks and the single quotation marks protect things from the shell. So for example, if you have a command with a space in it and you don't want the shell to interpret the space as breaking that into two commands, you can use inverted commas. The back quote mark, which is this one I'm just highlighting here, this is a special meaning. If you enclose a command inside that on the shell command line, then what happens is that gets evaluated first. Does that make sense? So you evaluate, you run the thing inside the quotes first, inside the shell then does whatever it asks, and the result is replaced into the command for the overall line. Does that sound strange? Well, we'll find out exactly what that does later. But just remember, back quotes, it's a different button on the keyboard and it does things quite differently. Usually a hash like this is a comment, and we'll get to see that in a lot of the examples I give. We're going to talk more about this, which is the pipe character, and these, which there's different context for these, but they're redirection characters. And they're used to send the information going into or out of a program into different places. It will all become clear. For now, just remember there's all sorts of meanings for these different symbols. So, as I mentioned, the vertical line is called a pipe, and the greater than or less than symbols are called redirections, and they're really important for gluing things together. So, as I mentioned previously, the shell does a lot. It holds the internet together. It underpins the information that sends your emails from one place to another, or looks up domain names for different computers. And a lot of that is done with this sort of command. And these commands on the left-hand side of the page are things that you can type into the Linux shell, and you can try them out. For example, I can show you if it works. I can pop up my Linux window in VirtualBox, and I can just echo hello, and it will print hello to the screen. And I can echo hello, so using the up arrow to repeat the previous command, and redirect it into something called hi.txt, which creates a creates a file called hi.txt in the current directory. And if I cat or read that file, what cat means send it to the display, we can see it contains the word hello. So all of these things you can do in the command line. If you're using an Apple computer, you can also do it in the Apple terminal. So I'll see if I can get that up. Right, so this is an Apple terminal window. You can find this in Applications, Utilities folder. And I could do exactly the same thing. There's nothing in the current directory. I can do echo hello world. I can redirect that into a file if I want to. I see the file in that directory, and I can read out the file there. So if you're using Windows, you should be able to get a bash terminal, or there's some advanced Windows terminals that you can use that will do something quite similar. So let's move on from there. I talked about the single redirection here. It takes what would normally be printed to the screen and it redirects it into a file. If that file doesn't exist, it creates it. Now if I did a second one of these, echo hello redirect into hi.txt, if I replaced it echo world redirect into hi.txt, then it would recreate a new file, hi.txt, that contains the word world, and it would overwrite the one containing the word hello. And if you don't want that, if you don't want the echo to overwrite the previous file, if you wanted to add something to the end of the previous file, then you use the double redirection symbol here, and it concatenates the new text at the end of the file. As I mentioned, I wanted to look at it on the screen. I can use cat and so on. I can also use cat, and instead of putting that on the screen, I can pipe the output. So instead of going to the screen, it goes into a program, and there's a program called WC. Yes, really, it's a program called WC. It's actually quite useful. And if I did this, I cat the content of the /var/log. It's in the directory var log syslog file, and I pipe it into the program WC. Or I could take our hi.txt we've just created, and I could pipe it into the WC program, and that would display something on the screen. It would display the output of the WC program given the input from that file. Or I can take the output of the WC program and I can redirect that into a new file called out.txt, creating a file called out.txt. You can try this yourself. There's all sorts of things you can do at the command line. It takes a little while to get used to it. What I mean is that if you get the spacing wrong, or you accidentally use a capital letter as a program, because it's all case sensitive, then the shell will complain. It takes a little bit of trial and error to get the thing working as you want, but it won't take long. A few minutes before you get comfortable with what you're doing. So we talked about these redirections and these pipes. Just want to backtrack a little bit just to understand what's actually happening here, because it's important. So any program that you run has some input and some output capabilities. Okay? Now sometimes programs, they don't actually look at the input. That means maybe a program just generates something, like it plays music. It doesn't need to look at the input. And sometimes a program seemingly has no output. It just receives things coming in, like it records your key presses. But all programs have the capability to have an input or an output if the programmer has decided to use that. Okay? The input and the output, they're called streams. So there's a stream of data coming in and a stream of data going out. In whatever language you're using, if you use an input command or a print command, then that will either access the input stream or will create an output stream. That's how it works. In actual fact, you can have multiple input streams and multiple output streams. In Linux, there's 3 default streams. There's a standard input, a standard output, and a standard error output. So every program can do this. And inside your program, if you're writing C, if you have a scanf command, it reads from standard in. If you have a printf command, it reads from standard out. If you see, you can do an fprintf command, and you fprintf to standard out, file printf, or fprintf to standard error, and you can output to the standard out or standard error streams. We notice also from this diagram that they've got numerical identifiers, stream 0, 1 and 2 respectively. If you open a file for input and you open a file for output, you're actually creating more streams, in this case 3 and 4 respectively, or if you did it the other way around it would be 4 and then 3. So anytime you do that, if you fopen 10 output files, then there'll be 10 streams, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now, we've seen that that's what the program does normally. If you type at the keyboard when you're running a program, it will take the things that you type into the standard input, and if the program prints something, it will print it to the screen. So what redirection is doing, what piping is doing, is it's redirecting and directing these different streams. Okay, and this is not changing your program. The program code written in C or Java or C++ or whatever you want, this doesn't change. It's the same program, but it's how you run it. So this is executing my program. If I just executed that, just this little bit that's circled, then the program would read stuff from the keyboard and it would write stuff and print it to the screen. But I'm using a redirection on the input just here. I'm redirecting something from a file called input_file, and I'm redirecting that to the standard input, and that's what this command is doing. It means that whatever text is inside that input file, the program will receive it just as if I typed it at the keyboard. And we can redirect the output. We don't need the 1 here, it's default anyway, but we're redirecting the output to output file. So whatever that program would normally print up onto the screen is now being captured and put into the output file, and it's not shown on the screen. If I've got some error in my program and my program crashes, numerical error or stupid programmer error or whatever it is, then that information will be written normally to the screen, but I'm capturing it and putting it into a file which I've called error_log. And if you're running these programs non-interactive, like in a batch mode, so you're doing it without you at the keyboard, you want this to happen when you're off sitting on the beach somewhere, then you would probably want to capture all of the error messages. Nobody's going to see them on the screen. You can capture them to a file and look at them later. It can get very, very complicated. This is not complicated, but it's more complicated than the last example. We're actually running 2 programs here, program 1 and program 2. Each of these programs, it's got the default 1 input stream and 2 output streams, numbers 0, 1 and 2. And what we're doing is we're running program 1, we are redirecting so that it gets its input from something called inf, it's a file on the current directory, and we're redirecting its error output to a file called ERL. Meanwhile, we're piping its standard output to the input of program 2. And in program 2 we are not redirecting its standard output, it's going to the screen as normal, but we're redirecting its standard error output to the same ERL, error log. Okay? So the command down here is a proper shell script and it does what the picture shows. Of course, it requires that there is a file called inf in the current directory. If you try and do this and the file doesn't exist, then of course the command will not work. But it will create ERL if that doesn't already exist. So this is how we generally do it, and in practice we build this up bit by bit. So when you're doing things at the command line, at least until you reach guru status, which I'm not at, but when you try this, you build it up bit by bit. You start off with program 1, you check the redirections are working. If it's all good, then you pipe it to program 2. You check the redirections are working, and check the redirection for error, and then test it. Always you try it, you test it, and build it up bit by bit. It might sound complicated, but there's some really good reasons why you would do this sort of thing. Okay? If you don't redirect something, if you don't redirect an output, it will pop up on the screen. Now your screen can rapidly fill up with text. Sometimes when you boot the computer up, you can see all the text running past. You can't read that. If you wanted to actually read it, you would redirect that into a file and look at it later. The input comes from the keyboard. Well, yes, if you want to have a program that every time you run it, it says, are you sure you want to do this? Yes, enter. Are you really sure? Yes, enter. Are you really, really sure? Yes, yes, enter. If you don't like that, just create a file with yes, enter, yes, enter, yes, enter. And instead of running your program, run the program with the file redirected into it. And then you don't have to type yes, yes, yes. Why we do this? There's many reasons. It makes life a lot easier in practice, but it's also extremely efficient. Okay? And we saw this example that was shown with the two bubbles earlier. It's running program 1 and program 2. A really important thing here is that program 1 and program 2 are multitasking. They're running simultaneously. There's lots of ways to multitask on Linux, but this is probably the easiest. Just think about this for a moment. If you didn't multitask, then what you'd have to do is you'd run program 1, it would read the input file, program 1 would execute, and it would create an output file. And the output file would get bigger and bigger and bigger and bigger and bigger. And then when program 1 finished, you'd say, okay, now let's run program 2. And you'd run program 2, it would take that big file and process it and create its own output. Now what happens if you're dealing with data that's massive? If you've got a 1 terabyte file? Okay, so you're going to run program 1 and it's going to create a 1 terabyte file, and then you're going to run program 2, it's going to fill your hard disk up. But if you do it like I've shown here with the redirection and piping, the way it works is that program 1 processes a couple of bytes. When it's finished processing a couple of bytes, it sends those to program 2. Program 2 deals with that couple of bytes while program 1 creates the next couple of bytes. And you can stream things, and your hard disk never becomes full. It never needs to create a 1 terabyte file. So if you're dealing with continuous data like video data or sound data or internet packets, rather than creating massive files, just stream the data as it comes in, a few bytes at a time. And it's extremely efficient. Okay, so we looked at this feature of a shell, which is to the redirection and piping. We're going to look at a few other features of the shell. The shell script is not the most user-friendly language ever around, but it's very capable. And like all programming languages, it can do conditionals. It's an if. And in the example I've drawn in the square box on the screen, I'm doing if, and then I run a command called test. Now test is a built-in command that can test many things. In this case I'm giving it the -f flag. So the test command is checking if there's a file called tcp_log which exists in the current directory. If there is, then it echoes, so it prints this thing to screen. TCP server is running. Else, if that file doesn't exist, I'm doing another test, test -e. -e exists. Okay, so I'm testing if an executable exists, which is called TCP_server, and that executable is in the directory /usr/bin. So if that executable exists, that executable is a program you can run, then I execute that program. Otherwise, I just print something, TCP server not found. Fi is the end of the if. If fi. If, elif, else, fi. Or if, elif, fi. And you can build up quite complicated, nested conditional statements in this way. Note the syntax here. If something semicolon then, and then I typically put the command on the next line. And you can concatenate this so everything goes on the same line. It's not very readable then. And you can also have it shorthand programming. So this thing, if test -f, you can actually replace test -f with just this square bracket -f and the closing square bracket there. This is a shorthand way of doing a test. If you're in the shell, you can type help test, and you can see how the test command can test for many different conditions. It can look at text, it can look at numbers, or it can see if files exist or directories exist, and so on. Very capable. Not very user-friendly though. So as everything I say, just try this out in the command line, build it up if you want to use this. You can do anything that you want, but it might not be obvious how to make it work. Looping is there as well. If we want to loop, there's many ways of doing it. Textual loops are easy. So this example in the square box at the top, it's saying wildcard.txt. So what's that mean? That's looking in the current working directory for every file ending in .txt. So for every file, it loops around and assigns it to the variable text file. The text file is a variable. So let's say there's 5 .txt files in your current directory. What this will do is it will print found1, and it will have the name of the first file, and it will loop again, print the name of the second file, loop again, print the name of the third file, and so on. And each time around the loop, it assigns a new one of the things it's found to the variable text file. And here we see the use of the $ symbol. The $ means the variable text file. So when you want to read what the variable text file contains, you put a $ in front of it. There's also while do looping. Again, the syntax is similar. While some condition, semicolon do, semicolon command, and semicolon done. If you put the command on a new line, you probably don't need a semicolon. Something to experiment with. And there's a case statement. This is really weird. C has a case statement. Some languages don't. But note the syntax here. So do, case, ESEC is case backwards, and then done. Why don't they have odd here? OD. I don't know. But the syntax is odd. I've got a closing parenthesis here, and then double semicolon at the end of the line. It's pretty weird. But one thing is, it's really easy to read this. If you see this in a shell script, it's actually pretty easy to understand what's going on. You can guess very much. I'm not going to ask you to try and do a case statement though, because the syntax, the spacing, and the closed brackets and so on is a bit fiddly. Just know that it exists for now, and it's a good option if you need it. Alright, You know what to do now. It's time to stop. Part 2 of the hands-on Linux lab is it's pretty much going over some of those things I've just talked about, and at the end you'll also use an editor and you'll create a simple C program and compile it, and you'll need that for later, but for now just to know how to compile a simple C program in the shell. So please stop, do the hands-on lab, and then join me a little bit later. Welcome back. I hope that went okay. We've got a very short section now. I'm going to talk to you just for a couple of minutes, but it's an important couple of minutes. So when we talk about shell programming, we talk about the things that we've been looking at previously, and the types of commands, the redirection and the piping and so on. But there's lots of helper applications that go along with the shell. So when you talk about the shell, people usually consider these as being part of the tools that you would use for shell programming. There's lots of helper applications. We used ls, we've used wc, but the big three are probably grep, sed and awk. So grep searches for regular expressions. It doesn't sound very useful, but it is extremely useful. It's also very fast. If you wanted to search through a terabyte of data, this is how you would do it with grep. Sed is an editor, so rather than just searching for things, it can modify them. So it can search for regular expressions and modify the regular expressions. It can do this in files, but it can also, like grep, it can do this on streams of data. So if you have a continuous stream of data, for example, somebody's web searching history that continues on and on and on, or in fact the web searching history that's coming in live from a large company, you could use grep to search for particular websites that people are accessing. If you didn't want those websites to be public record, you could use sed to change the names of some of the websites. So that's grep and sed. Very useful. Not the most easy user-friendly programs, but when you get used to them, it's okay, and you can do some of the most common tasks reasonably easy. If you wanted to access the more involved or the more powerful features of both, then there's quite a lot of depth there. You can really go as deep and as complicated as you want, but just to use them is really easy. Awk, on the other hand, it's sometimes people consider that the awk program, the name came from the word awkward, which is something to say for the complexity of using this. And the programmers, they describe this as a programming kit for analysing and manipulating text files. AWK are the names or the initials of the surnames of the people who invented this language. K is Cunningham, one of the co-inventors of the C programming language. Now what awk is very good for is column-based data. That is data which is streamed, and it comes with one record per line, but each record is separated maybe by a comma or a tab or something else, and you can search through and modify this data which is streaming line by line with number of records. It's really very powerful. Like I said, just using grep and sed is pretty easy, and here's an example of how to use grep. There's many ways of using it. One thing about Unix commands, Linux commands, is that you can use them in many different ways. There's lots of different ways of accomplishing a given task. So this is grep, means it's searching for the word root. It doesn't have to be in inverted commas. Like I said, you'd use inverted commas to protect something from the shell. For example, if you're searching for something with a space inside it, or some weird character inside it that the shell thinks means something. So right now we're searching for the word root. Where are we searching? We're searching in a file called syslog, which resides in the /var/log subdirectory. And it will search for any occurrence of the text root. So any line inside the system log file that contains the word root, it's going to print it to the screen. We already know that the cat command can print the contents of a file to the screen. So what this cat command does is it prints the contents of /var/log/syslog to the screen, and we already saw the pipe character, so we can take that's supposed to go to the screen. Instead of sending it to the screen, we can pipe it into the grep program, and we can tell grep to search for the word root in the stuff that's being piped in. And this does exactly the same thing as the previous command. It's just illustrating what you learned previously with the pipe character. We can use the pipe character to send the output of grep somewhere else. In this case, we are piping the output of a grep command, so it's grepping for the word root in the /etc password file. Anytime it finds that, any line in the password file where it finds the word root, it will print to screen, except that we are piping that. Instead of printing it to screen, we're sending it into the sed program. We're using a -a, we're using extended sed. It's typically what you would use. And we're telling sed to do something, and sed's command is inside these inverted commas here. And when you get to know sed, you'll know that the first thing just here tells you which sed command you're operating on. In this case it's an S, it's a substitution command. And this is saying, sed, anytime you see a colon, substitute it with a star. And you be greedy about it. Greedy means that don't just do the first colon, do every colon. Let's have a look at that. First of all, we can grep the word root from the etc password file. It comes up once. The password file is the UNIX system file that contains everybody's passwords. Don't worry, they're actually not used like that these days. The passwords are now in something called a shadow password file, which you can also look at just incidentally. But they are now protected from normal people. But in the old days you'd get the passwords in the password file, which is quite interesting. But we now still see the user, so every user on that system has got an entry in the password file. And root is the one user that every system has, so we're looking for the root user's entry in the password file. Now we can search this and print it to screen, but I want to pipe it into the sed command. And we're going to pipe it into the sed command. We're going to substitute every colon with a star, and we'll do it greedily. And we get that. If we didn't do it greedily, we only substitute the first colon to be a star. Does that make sense? I'm going to try some of these later. Sorry, we're back. And you're going to build up some more complicated commands. This is a two-part sed command. We substitute the word root with the word Fred greedily, and then we substitute the colons for stars. So this two-part sed command, the parts will run one after another. Like I said, build it up gradually. Anything you do in the shell, build it up gradually. Even you see the way I did it, I searched for the word root in etc password. I did the first the first clause in the command, and then I tried to do a pipe character, and then I built up the sed. And if I built this command here, I would start with the first part of the sed command, I would check it's working, and then I'd add the second part of the sed command. Build it up gradually. Don't try and do everything at once. It's destined to fail. Now we talked about regular expressions a few pages back. I said that grep searches for regular expressions, sed edits or substitutes regular expressions. Many Linux or Unix commands use regular expressions. You know, if you're using a word processor like Microsoft Word or OpenOffice, or if you're using a web browser like Chrome or Firefox, you can do Control F or Command F and you can search for something in the page. So I could search for my name, in a page of text. But what if I wanted to search for misspellings of my name? Especially my surname, McLoughlin, is quite long. What if I wanted to search for people who've misspelt it? That maybe they put an A instead of an O inside my surname. Well, I could just search for McLoughlin spelt correctly, and then I could do another search for McLoughlin spelt incorrectly, but there's so many ways of spelling it incorrectly, that's quite exhaustive. In UNIX, I would just search for a regular expression, and I would look at all misspellings of my surname, and I'll find out how to encode that in a regular expression. So the common ones are, when we're searching for regular expressions, we can search for my surname, McLoughlin, but we could search for MCL dot, and that would be MCL followed by 3 characters, and any characters. So dot is a wildcard. A question mark means that the preceding thing, the thing before that, is optional. So MCL question mark means that it will search for anything with MCL, but also anything with just MC. Okay, I can search for something which is optional, and something which can be matched 0 or more times, or 1 and more times. And in fact, I can specify how many times it searches for. If I wanted to search for MCLO or MCLA, I could search for MCL square brackets OA, close square brackets, and it would search for MCLO or MCLA. And inside the square brackets I can have a range of characters. I can build up command bit by bit. It's really hard to understand everything about regular expressions by just reading about it in a book or looking at it on a lecture slide. You need to do it, you need to try it. And the way is do baby steps. You start off by trying something simple, the dot, then you try a question mark and build up. Experiment. See what you can do. Try some of these examples down the bottom. Try some of the examples in the hands-on lab we're about to look at. There's more regular expressions here. In text files, things tend to be line-based, so you have a line of text, enter or return, another line of text, return, another line of text, return. And when you're looking for regular expressions inside this sort of text file, then the caret symbol, which is this up arrow here, it means beginning of a line. So if I want to search for my surname, McLoughlin, but only when it's at the beginning of a line, I would use caret McLoughlin. But if I wanted to search for my surname at the end of a line, I would search for a regular expression McLoughlin $, because a dollar indicates the end of a line. As I said, square brackets can search for a range of things, and inside the square brackets you can search for something except something else. So this searches for any letters except for A, C, D, E and F. The curly brackets search for something a number of times, or a number of times and more, or between a number of times, so I can search for something between 2 and 10 times. And I can search for things at the beginning of a word or an end of a word. A word is something that begins or ends with a space or a punctuation character. It's really powerful. You can literally search for anything with like regular expressions, as long as it's text-based. So you're going to try that. Try a bit of hands-on stuff. Enjoy this. It's actually really, really fun. So welcome back. I hope you've had fun doing that. Using regular expressions and grep and sed is a really good way to impress your friends. That's assuming you have geeky enough friends, and you have, right? Your friends are geeky. If not, you need to go and make a new set of friends. But anyway, you've mastered that. But if you have really geeky friends, then you want to be getting good at awk. Like I said, awk is awkward even for computer people. But it is extremely powerful. We haven't done any awk in the hands-on session just gone by. There'll be a small amount in the next hands-on session. I just talk about it just on this one slide, just a little tiny bit. And just to show you, just to convince you how awk is amazing, we know what's happening in the first part of the command shown on the screen, that cat/etc password. It's taking your password file and it's sending it to the screen. We pipe it into the awk program, and the awk program is doing something which is just here, and what it's doing is it's printing $1 and $7. Okay. Well, print is a command. It prints something to the screen. What $1 is the first column of data. So the etc password file contains a number of lines of text, and the lines are separated by what? By colons, ... right? We saw that because we replaced those colons earlier. And this is saying that awk is separate every line at the colon, and the bit before the first colon is $1, the bit before the second colon is $2, the bit before the third colon is $3. So it takes the first item on the line and the seventh item on the line, and it prints them out for every row of text in the password file. That's good, makes sense, but it doesn't quite tell you how powerful this is. I've got another example below. It's doing list all the files in your directory, and -l. -l is a long format of listing. Normally you do that and it will print the stuff to the screen. But what this is doing is it's piping it and sending it into awk. And awk is creating a variable called size, and each line, it's taking the variable size and it's adding the content of column 5. So when you print ls-l, there's columns of data. For each row, it's taking the 5th column and it's adding that to the variable size. And when it's done, it prints the size. What this is going to do is it's going to print the size of every file inside your subdirectory. It's an easy way of summing up all the files there in terms of the number of bytes that they contain. But even that doesn't really tell you everything that awk does. Imagine you've got a terabyte file of data, and you want to do something where for every line, if the first column in a line has got a particular name, then take the 5th column in that line, subtract it from the 3rd column in the next line, and if the line after that happens to end in something, then print it to screen. You can build up very complicated rules with awk. I really can't emphasize this enough. It's a bit awkward, so you build up the commands gradually. You try it on the command line. You build it up gradually. Like anything in shell programming, whatever you do on the command line, you can save it in a file and run it as a shell script later. Okay, we'll move to something completely different. It's the UNIX process model. It's another one of the advantages of using Linux. A process is usually just a program. So when you run a program, it launches a process. Actually, you can have one program that launches multiple processes, and every time you run a program, a new process or multiple processes created. So generally, there are a large number of processes happening at any one time. If I was just to pop back to my Linux screen here, clear away what I've done previously, I can type PS to list the processes happening in my system. These are processes that I own, or PS AUX lists everybody's processes, and you can see there's quite a lot of processes there. Starting with process number 1, it's down here, and my current process is about 3,293. So that is the list of the running processes. I can run a program like this, and until that program exits, it occupies the the shell. When the program exits, when I press Control-C, then I can type something else. Let me just show you exactly what I mean. I'm going to use the excise command. Most Linux computers, they contain excise. It doesn't do very much, but as you'll see. I take the command and press Enter. Right, so what it's done is it's given me these eyeballs down the bottom of the screen here. That's all excise does. It follows my mouse pointer. But I can't type anything here. I can't run any commands because excise is capturing all the input from the keyboard. So this process is running. If I create a new tab, I can list the processes. I can list my processes PSAUX, and down towards the end I can see the excise process was launched. It's running by me. My username is Asian. That's because I used to work in a school of applied science, so they gave me my first name Ian and the school of applied science AS. It doesn't mean that I'm actually Asian. But you can see the excise command is running with process ID number 3297. I can press Control-C and I can quit the excise program. And I go back to this tab, repeat my PS, and excise has disappeared. So this is just telling you a little bit about Linux processes. And we're going to try some of that in the hands-on session that follows. When I ran excise, incidentally I didn't need the / at the beginning of excise because it's stored in a place in the path that anybody can access. So if I create my own program, I need to use / to run it. But with excise it's a built-in program, I don't need it. But if I use the ampersand, the AND symbol after excise, then it would multitask in the background, and I wouldn't have the situation where it prevents me from typing any more commands. So again, we'll try that in the hands-on session. Job control allows you to switch programs that are multitasking, bring them to the foreground, so they're not multitasking, they're hanging, they're holding on to the foreground in the computer. We can send them to the background to run in the background, or you can freeze them. It's quite a powerful aspect of UNIX. I've seen the Control-C command. It kills a program that's running in the foreground. And there's actually a command in UNIX called kill, and you can kill programs in different ways. It can be quite fun. You can try that out in the job control part now. So I hope you enjoyed that. I hope you enjoyed your foray into Linux and Unix job control. You've actually covered a lot of stuff. You're probably not experts at the shell now, but you've got everything you need to know to find out more and to start to grow in this. Shell scripts really do hold the world together. They underpin so much of what's going on out there. They're used in industry and commerce extensively. Being good at this is a real skill for life. So please continue to experiment, learn, develop on your own. And if you do have any questions, feel free to track me down and I'll see if I can answer these. But it won't be long before you become much better than me at doing this sort of stuff. So enjoy and thank you.